We have a plane flying 650 miles an hour in a bearing of 175.3. A 25-mile-an-hour wind from the direction of 266.6 degrees blows against the plane. Find the resulting bearing of the plane. Okay, the hardest part here is drawing the picture. You might be awesome at it. I tend to suck at it. Okay, so we're going to start by drawing this picture here. So here's this is 90 degrees east, so down here's north at 0, here's 180, and here's 270. So our plane is going this way, okay, at 650, and this is 175.3. Okay. Then we have a 25-mile-an-hour wind from 266. So 266 is right here. Okay. And this is my 25-mile-an-hour wind. That's at 266.6. Okay. Now this is pulling it this way. So our resultant thing, this is going to be our x. And we really want to know what that theta is, but we're going to get there. Okay, that's our goal. We want to know what the adjustment's been made so we know what bearing this pilot is actually flying at. We're going to have to find the ground speed, though, here, too, as part of our quest. Okay, I have a lot of things written on here. What do I know? Well, what I'm going to draw in is I'm going to draw in my parallelogram right here, okay? So this is 25, this is 25, okay? So I've got my two sides. I need to figure out, though, what that angle is, and I'm going to kind of work my way there. So the difference here between 270 and 266.6, okay, is, I think 3.4, but yeah, 3.4. That also means this is 3.4. Remember back from chapter 1 and we had all those rules about, congruent angles and, parallel lines, blah, blah. That's useful. These are vertical angles. Therefore, they're the same. I can also figure out what this is. This is 180 minus 175.3. This is 4.7. So using both this information, so this here, okay, so this angle here, okay, that's my 175.3 minus 90, that's 85.5. And then I have to add in that 3.4. So this angle here is 88.7. Why is that useful? Well, because our parallelogram here, this one has to be 180 minus 88.7, or 91.3. Now I finally have enough information to use law of cosines to find x. X squared, my vector, so the new ground speed of this plane after this adjustment is going to be 650 squared plus 25 squared minus 650 times 25 times the cosine of 91.3. Okay, so now I'm going to get out my calculator and I'm going to plug this all in and find out how fast this plane is actually going. Okay. Okay, so I've got all my information. I want to know how fast this plane is actually going. So 650 squared plus 25 squared minus parenthesis 2 times 650 times 25 times the cosine of 91.3, and then take the square root, not of a negative sign. I want the actual answer. So this plane is actually going 651 miles an hour. Okay, now I need to go back and using this information, so I know that x is 651.05, something like that. But I'm going to leave it in my calculator, so that's not going to matter. Now what I have to do is I'm going to use law of sines to find this angle I wanted. So I want the sine of theta here, that theta, and it's opposite 25. And now I know that the sine of 91.3 is opposite this 651.03 or whatever it is. So now getting my calculator back out, I want to just to be able to use that. So I'm going to do 25 sine of 91.3 divided by my answer. Okay, so this is the sine of theta equals this. I'm going to take the inverse sine, and I get 2.2. This is my adjustment. So I was at 175.3. This plane got moved over 2.2 degrees. It is now at a bearing of 173.1. So theta here was 2.2, but our actual answer is going to be 175.3 minus 2.2, which is 173.1. This is the new bearing of my plane. This is all about getting the picture drawn and visualizing the picture. Once you have that picture drawn, you have the wind correction angles, and you can draw out that parallelogram. The problem's not hard. It's just using the formulas. The hard part is going to be getting that picture set up and getting it drawn correctly, and that's going to take practice.